numerical integration. So in this section, what we're going to look at is how to evaluate things called non-elementary integrals. And these are integrals for which we can't express their antiderivative as a finite combination of elementary functions. So some examples of non-elementary integrals are these. For example, look here, sine of x squared. I cannot find a finite combination of functions to say it's my antiderivative. And that's really surprising because that's a pretty simple function and pretty straightforward. Similarly, we can't find 1 over the natural log of x or sine x over x. So what are we going to do if we have one of these integrals and we need to evaluate it? Well, what we're going to do is we'll estimate the area under the curve. And we're going to use a method called the trapezoid rule, which involves, instead of using rectangles, using trapezoids. So if we take our curve and look at the area under it, and we subdivide it into n subintervals, you can see that on each subdivision, it kind of looks like a trapezoid. We have parallel lines here, and then a straight line here, and this is pretty close to a straight line right here. So it looks like a trapezoid. So the area of a trapezoid is equal to 1/2 its height times the sum of its bases. And if we look at the kth slice, this one right here, the height of the trapezoid is the distance between the two parallel lines. So that distance is what we call delta x sub k. And then the bases are, well, here's one base, and we know the length of that. That's f of x sub k minus 1. And then here's my other base here. We know how long that is. That's our f of x sub k. So using this idea, we get that the area under the curve on my kth slice is approximately equal to 1/2 the width of that interval plus our y sub k plus 1 plus y sub k, where this represents our function evaluated at x sub k minus 1, and this y sub k represents f evaluated at x sub k. So it's just the height on either end of your subinterval. All right. So to make our calculations easier, instead of talking about intervals of varying width, we're going to assume they're all the same width. So we'll call it delta x, which is b minus a over n. And then now we can say that the area under the curve is approximately the sum of all the areas of those trapezoids. And if we just reorganize that, pull out the 1/2 delta x, it's equal to this. And now when you look at this sum, look, it goes y naught, and then I have 2 y1s here. Then I'll have 2 y2s here, and so forth until I'll have 2 y sub n minus 1s here, and I'll be left with only 1 y sub n at the end. So using this idea, we come up with the trapezoid rule, which says to approximate the integral from a to b of the function f of x, we're going to use the value t, which is equal to delta x over 2, y sub naught plus 2 times y sub 1 plus 2 times y sub 2, and so forth up to 2 times y sub n minus 1 plus y sub n. And this is where delta x is b minus a divided by n. X sub k is going to be the partition points, and our y sub k is our function evaluated at the x sub k. Now, one thing to notice, well, actually, there's two things to notice. The first is all the terms in here are multiplied by 2 except for the very first one and the very last one. The second thing to notice is how many terms are in this sum. Well, there's 1, 2, 3, so forth. There's n here plus 1 more. So there's n plus 1 terms inside your parentheses here. All right? So let's see how to use the trapezoid rule. Let's approximate the area under the curve 1 over x from 1 to 2. All right? We know how to integrate this, but let's use this as our example. And let's do it by using the trapezoid rule with n equal to 10. So here's the integral we're trying to estimate. we said that we're going to let n equal to 10. Our function is 1 over x. Our interval AB is 1 to 2. And that tells us that delta x is equal to b minus a over n, which is 1/10. That our x sub k's are going to be equal to 1 plus k over 10. And our y sub k's are our functions evaluate our x sub k's. So that's 1 over x sub k, which is equal to this. We just plug in x sub k here, and we multiply top and bottom by 10 to get y sub k is equal to 10 over 10 plus k. So now we take all this, and we plug it into our formula for the estimation. So we said delta x was 1 over 10, and then here's our y naught here, and then 2 times our y1 plus 2 times our y2, and so forth until we get up to 2 times y sub n minus 1, which is 9, and then only 1 times our y sub n, which is y sub 10. So now if you take the sum and you simplify it, you'll get that this is approximately equal to 0.69377. And note that if we had gone through and integrated this like we knew it would, we would have gotten natural log of 2 minus the natural log of 1, which is about equal to 0.69315. So this is a pretty good approximation.